Welcome to this next video in which we are discussing the dual of a vector space. So I apologise for the abrupt ending to the previous video. There was a problem with the camera. However, we got up to the point where we have proven that there is an additive identity in our dual vector space. Again, this will be the linear map, which we call 0, the 0 map, which sends all the elements of our original vector space, capital V, onto the additive identity in the field, 0 in the field. Okay, and we've discussed the fact that that 0 covector in our dual vector space will in fact add to all other covectors in the dual vector space to give that other covector back again. Okay, so we do indeed have an additive identity for our dual vector space. What we're now going to do is try and show that we have additive inverses in the dual vector space. Okay, so axiom number 4 then that we need to check that addition is going to obey. If I take an arbitrary covector phi, which is an element of my dual vector space, what I would like to show is that there exists another vector in the dual vector space which we'll call negative phi, the additive inverse of phi, which is also in the dual vector space, such that if I add phi and negative phi together using the addition law that I've defined on the dual vector space, so this addition is addition in the dual vector space, it will give me the additive identity back again, so it will give me the 0 covector, so the map that sends all elements of the original vector space capital V onto 0 in the field, and it needs to be true the other way around as well. So if I take negative phi and add it to phi, that also needs to give me the 0 vector. Okay, where again this is addition in the dual vector space and this is the 0 covector. Okay, so I want to try and show that if I have any linear map then that's in my dual vector space, that there is another linear map such that this is going to be true. Okay, so how am I going to do this? Well, let's just decompose this a little bit more. Okay, so let's just take one of these initially. Let's take the top one. Okay, the other one will follow very naturally from the top one. So let's take phi plus negative phi is equal to 0. Now what does that mean? That means the mappings are equal to one another. So this will map V from the original vector space capital V onto exactly the same thing as 0 would map V onto. But we know exactly what 0 maps V onto. The answer is 0 in the field. No matter what V is equal to, this is equal to 0 in the field. So we can instantly replace this thing with 0 in the field here. Okay, so we need some other mapping, negative phi, such that when I add phi to negative phi and then look at that mapping, it's going to map all elements of the vector space, capital V, onto 0 in the field. Okay, so now let's just apply the definition of addition of two mappings in the dual vector space, and what we'll get is that this is equal to phi of V plus actually no, this is fine, negative phi of V, okay, and this needs to equal 0 in the field no matter what V you put in there. Okay, so I'll remind you that this addition here is going to be addition in the field by definition of how we've defined the addition of the covectors in the dual vector space, and this is going to be 0 in the field. So that needs to be true no matter what V is equal to. So this needs to be true for all V is an element of our vector space capital V. Okay, now what does that mean about this thing here, negative phi of V? Well, that tells us that negative phi of V must equal the additive inverse of phi of V, and I know this looks really trivial, that negative phi of V is equal to negative phi of V, but these two things, I mean different things by these two things, hence why I put the brackets in different positions. This means the additive inverse of this map phi in the dual vector space, then acting on the element V in our original vector space capital V. This means the mapping phi acting on V, and then that will be some element of the field. Take the additive inverse in the field. Okay, so if you like, this is the additive inverse in the field, whereas this is the additive inverse in the dual vector space. So what we want it to be true, we want it to be true that the additive inverse of V in the dual vector space is going to map all elements of the vector space capital V onto the additive inverse of what phi maps them onto in the field. Okay, so we want this equation to be true, and if that equation is true, then this thing will be true, and it will therefore be true that these two mappings, phi and negative phi, will add to each other in the dual vector space to give the additive identity in the dual vector space. Okay, right. So what we need to do then is check that this negative of phi of v actually is going to be a linear map. So I want to check that if we do define negative phi of v to be this, that it actually is going to be a linear map, so it is going to be within the dual vector space. So let's just make sure that this does obey the criteria to be a linear map. Okay, so firstly what I want to do is check that negative phi of v plus v bar is equal to negative phi of v plus negative phi of, negative phi of v bar, like so. Okay, where, remember, this will be addition in the vector space, whereas this will be addition in the field over here. Okay, so how am I going to prove that then? Okay, well, I will apply the definition of what negative phi of an element is actually equal to, and I'll say that this thing here is just going to be equal to the additive inverse of phi of v plus v bar, and then I can use the fact that phi is a linear map here. Okay, so again, this is addition in the vector space capital V. Okay, now what I can do is apply the fact that this phi is a linear map, i.e. it's an element of the dual vector space, to split this down into negative phi of v plus phi of v bar, where this addition here is now addition in the field. Okay, so this is addition in the field here. Now, what we know is that if you have negative of something like this, this is effectively multiplying by -1 in the field. Okay, and multiplication distributes over addition. Okay, so what this becomes is negative phi of v plus negative phi of v bar, like so. Okay, where again this is addition in the field. Okay, and these negatives here, these are the additive inverses of these two things in the field. But then just applying the definition in reverse again, we can say that negative phi of v is negative phi of v. So this thing here, we're going this way this time. We're taking this and going to this. So this one is the same as this, and this one here is the same as this one here. Okay, so we can replace those two like that, and that's how we can get to that. So indeed, it's looking good that defining it this way is actually going to obey the criteria for being a linear map, and therefore it will be in the dual vector space. Okay, the next thing we need to check, of course, is that negative phi of c times v is the same as c times negative phi of v, like so. Okay, so it shouldn't matter whether you first scalar multiply and then apply the mapping, or you first do the mapping and then scalar multiply. Okay, so this will be scalar multiplication in the vector space, and of course this will be multiplication in our field here. Okay, right. So how am I going to prove this? Well, once again, we're just going to apply the definition. Negative phi of c times v, we'll just apply the definition here, that is negative of phi of c times v, like so. Then we'll apply the fact that this is a linear map here to say that this is negative of c times phi of v here, and then we'll apply the fact that multiplication in our field is both associative and commutative. So we've got -1 times c times phi of v here effectively, and what we can do is reassociate it and then apply commutativity to get the fact that this is the same as c times -1 times phi of v, And of course then we can just apply this definition here in reverse to say that this is the same as negative phi of v. Again, that's how we can arrive at the fact that this does indeed obey that second criterion for being a linear map. So indeed, this negative phi of v defined to just carry all the elements of the vector space to the additive inverse in the field of what phi of v is, that is a linear map, and that is going to be the additive inverse of the linear map phi in the dual vector space. Okay, so we do have additive inverses in the dual vector space. Now, axiom number 5 then, because remember, we need addition in a vector space not just to obey the axioms of a group, but also to obey the final one, commutativity, to make it an abelian group. Okay, so we now want to check that phi plus, actually I'll put phi1 plus phi2 is equal to phi2 plus phi1. Well, again, this is a nice easy one to check. So we just need to check that those two mappings that we get by applying the definitions of how we've defined addition of two linear maps will be exactly the same. Okay, so what I want to prove then is that phi1 plus phi2 of v is the exact same map as phi2 plus phi1 of v, i.e. that these two maps will carry v onto the exact same thing for all v. So I want to make sure that that's true for all v as an element of the vector space capital V. And I'll try to continue colouring in here, so this is still addition in our dual vector space. Okay, right, so just by definition, the way that we've defined this map is that it will be phi1 of v plus phi2 of v, where this is addition in the field. Now, of course, addition in the field is commutative, so what I can do is just swap those two things right around and say that this is phi2 of v plus phi1 of v. Again, of course, this is exactly what you'd have got if you just applied the definition of this, so indeed, this is equal to this. Okay, so yes, it really does not matter what order you add two elements of the dual vector space together in, you will get the same covector as your final answer. Okay, excellent. So now we have checked all the axioms then that addition must obey. We have defined an abelian group structure on this set of all linear maps from the vector space capital V to the field capital F. Okay, so we're halfway there. What we now need to do is define a scalar multiplication, and remember, we want our dual vector space to be a vector space over the field capital F. So we need to define a scalar multiplication using the elements of the field capital F. Okay, and we then need to prove that that scalar multiplication on this dual vector space will obey the axioms that it needs to obey for this to be a vector space. Okay, so firstly let's just define scalar multiplication. So what I now want to do is define what is, so let's just take some element of the field, so let's say, let C be an element of the field capital F. Okay, and of course we'll have some element of the dual vector space as well, so phi is an element of phi star here. We now want to define what is C times phi. Okay, and this is going to be some mapping, so I want to say what is C times phi of v. Okay, now I'll continue trying to do my colour here. So this now is going to be scalar multiplication in the dual vector space, so that's why I'm colouring it in turquoise there. Okay, so not scalar multiplication in the original vector space, not multiplication in the field, scalar multiplication in the dual vector space. So how am I going to define this? Okay, well this is going to carry all vectors in my vector space capital V onto, and it's obviously a very natural thing to do, C times phi of v. So you just say, well, where did the mapping phi take all the vectors v to, and just multiply that by c, and of course this is an element of the field, so this must be multiplication in the field here. Okay, so coloured in purple there. Okay, so that's how we're going to define the scalar multiple of an element of the dual vector space. It's another mapping, another linear map, so it's, well, we need to check that actually. It's going to be another mapping. We haven't yet checked that this is going to be another linear mapping, but it will be. Okay, it's going to be another linear mapping in the dual vector space, and this is how it's going to be defined. We're just going to map all vectors onto what phi would map them, and then just multiply that element of the field by the scalar c in the field multiplication law. Okay, so that's the definition of how scalar multiplication is going to work in the dual vector space. The first thing to check is that this is closed. Okay, so axiom number 1 is closure, and what that means is that we need to make sure that this final mapping we've got here, c times phi, that this actually is an element of the dual vector space, that this is a mapping that is linear. Okay, so we now need to check that this obeys the two criteria for linearity. Okay, so what we need to check, criterion number 1 then, is we need to check that c times phi, where that's going to be multiplication in our dual vector space of two vectors v plus v bar here, okay, where this here is addition in the original vector space capital V, we need to check that that's going to be the same as c times phi of v plus c times phi of v bar, like so, where this here is addition in the field. Okay, and of course this is still addition in the dual multiplication in the dual vector space. Okay, right, so we need to try and prove that. So how are we going to do it? Well, we're going to start off just by applying the Veil definition. Okay, so this is all good practice. So now let's apply the definition here. So c times phi of v plus v bar, again just view v plus v bar as being one vector. It after all is some answer in the vector space capital V. Okay, so what we can then turn this into is c times phi of v plus v bar, just by definition, and this now is multiplication in the field here. Okay, but we've still got the addition there in the vector space, so that will be in red there. Okay, now what can we do? Well, we can apply the fact that phi is a linear map here, and we can therefore split this up in the way that we can with linear maps. So this will become c, and then it will still be times in the field, and now what we'll end up with is phi of v plus phi of v bar, and of course this addition here is now addition in the field. Okay, now what we can now do is apply the fact that multiplication distributes over addition in the field to say that this is the same thing as c times phi of v plus c times phi of v bar. Okay, where still all the multiplications and additions are in the field, but now rather than doing the addition first and then multiplication after, we've got multiplication first and addition after. Okay, and now what we can do is apply this definition again in reverse to say that this one here is the same as c times phi, where this is multiplication in the dual vector space, scalar multiplication in the dual vector space, so I'll put that in turquoise there, plus c times phi, again, multiplication in the dual vector space of v bar, like so, and that addition in the middle is still just addition in the field. Okay, so we're back then at where we wanted to go. So I've gone from here to here. Okay, so indeed I have proven that this obeys criterion number 1 of linearity. Let's now go to criterion number 2. Okay, so criterion number 2 of linearity says that what we must show is that if we take c times phi of c times v, and then, no, this is getting confusing now, we're going to have to pick some other symbol, so I'll use a times v here, okay, where a is just some scalar, again from the field, because remember, we're using the same field to multiply elements of the dual vector space as we are elements of the original vector space, so this is where it starts to get confusing. So that's multiplication in the dual vector space. This is going to be scalar multiplication in the original vector space, so I'll put red there. Okay, and we want to show that this is going to be the same thing as a times, in the field, c times phi of v, like so. Okay, so this is going to be multiplication in the dual space, and this is going to be multiplication in the field here. Okay, right, so that's what we need to show. That's the second criterion of linearity. Okay, so how are we going to do that? Again, just apply the definition. So c times phi of a times v is going to be the same, just by definition, as c times in the field, so I'll put a purple dot there, phi of a times v, where this is still multiplication in the vector space, scalar multiplication in the vector space. Now what we can do is apply the fact that phi is a linear map to turn this into c times in the field and then we'll have some brackets here, A, and again times in the field phi of v, like so. So I've just pulled the A out of the linear map here because phi is a linear map. And now what I can do is apply the fact that multiplication in the field is associative and commutative, so I can reassociate it so that I get C and A in brackets. Then I can commute it, so I can swap A and C around, and then I can reassociate it, so I can turn it into something of this form. So I'll turn it into A times in the field, C, and then again times in the field, phi of v, like so. So that's just applying associativity and commutativity of multiplication in the field. And then, of course, just reverse the definition now, and you can turn this into this here, because C times phi of phi, like that in the field, is just equal to C times phi in the dual vector space of v. Okay, so I can turn this into this. Okay, so indeed, that then is how we can show that when you apply this definition of scalar multiplication in the dual vector space, that the new thing that you get, this new mapping that you get, is a linear map. So scalar multiplication is going to be closed. You always are going to get another element of the dual vector space back again. Okay, now we'll have a break there, and in the next video we'll address some of the further axioms that scalar multiplication must obey. So we'll start off with associativity, then we'll go on to a multiplicative identity, and then finally the two distributivities.